I hope this is on. Find out. Alright, Chapter 5, Lesson 5, Independent, Dependent Events. Give you a little bit to write this down. Congrats, you now have access to beta. What? Try it now. Okay. But okay. Try it out. Ooh, fancy. 91.7% of people like my lesson 2, chapter 4, similar figures. I don't know how to look at. Alright. How do we use probability to predict the future? Same central question we've had all chapter. We're looking at independent, dependent events. We start out with independent events where one thing does not affect the next, which is really all we've been talking about so far. Hello, Mike Wazowski, also Eric. For example, if a letter is chosen and the spinner is spun, what is the probability of picking an E and also landing on an E? Got 5 letters here, and then a spinner. Any handle on it? Perfect. Completely random letters. I want to know what is the probability of getting an E on both of them. All we have to do here is we say what is the probability of either of these events happening. So if we start with the letters, we want what is the probability of getting letter E. So how many favorable outcomes are there? There's 2 E's here. There's 2 good outcomes out of 5 letters total. Okay? And then we go to our second event, our spinner, and we want to get a probability of E there. We do the same thing. We say how many E's are there? This time there's only one of them, still out of 5. Now we take these 2 probabilities, and here's the trick. If we want both things to happen at once, we're going to multiply the 2 together. So really all the math we're doing is multiplying fractions. So we go straight across. 2 times 1 is 2. 5 times 5 is 25. So what is the probability of both of these events happening at the same time? 2 out of 25. We find probability of each event, then multiply. And that's sort of what we did with sample spaces, only instead of having to list out all 25 possible outcomes and then picking the ones we wanted, we're just writing the ratios. That way it goes a little bit quicker. Okay? We don't really want to have to write out a list of 25 things to answer this one question. Okay? Let's try one more of those. Let's say we have a number cube and it's rolled twice. What is the probability of getting a 4 both times? So if we have a cube, here it is. We say, what are the outcomes you can get on this cube? Move this. Doesn't get. Oh well. So what are the different things we could get? We could get a 1, or we could get a 2, we get a 3, 4, 5, or 6. Okay. So what we want is we want to get the probability of a 4, and then we want to get 4 again. So since it doesn't change, no matter how many times we roll the die, we say these are independent events. Because both times we roll it, there's just one 4 that we can roll. So it's going to be 1 out of 6 the first time. It's going to be 1 out of 6 the second time. And then anytime we want two things to happen at the same time, we multiply them together. So 1 over 6 times 1 over 6 is 1 over 36. So what is the probability of rolling a 4 2 times in a row? 1 out of 36. Find probability each. Uh-oh. Ran out of ink. Oh, I think I ran into fair number cube. Fourth grade is the 7th grade. And we just do a lot of examples 7th grade with the 2 events, but we could go even further. If we want to know what's probability of getting a 4 3 times in a row or 4 times in a row, we could just keep multiplying the individual probabilities. Keep it simple for now. Alright, then our second part. Dependent events is just the opposite of independent events, where one event changes the possible outcomes of the next event. So one thing affects what happens for the second thing. And then our example is cards are labeled 1, 2, 3, 4, 5, 6 in a stack. We draw one card and then we don't put it back. This is the key word here. This is where you're going to look for to tell if it's dependent or independent. If it is not replaced, it means we didn't put it back. And then we draw a second card. So what is the probability both of them will be even? 7th grade. Like 8th grade, only one less. Alright. So our sample space here, we have 6 cards, so it's still possible outcomes 1, 2, 3, 4, 5, 6. So we say, what is the probability of getting even? And then another even. So if we do it the first time, we say how many even numbers are there? We've got 2, we've got 4, we've got 6. The probability of getting an even number the first time, 3 out of 6. So that doesn't change. That's what it's always been. Moving on, simple probability, independent. The first thing is always just what can happen. Right? But our second event, this is where it gets a little bit different because we have to assume that we picked one of the even numbers the first time. We don't know which one. We don't even really care which one it is. Okay? But let's say we picked, I don't know, 6. Okay? So if we pick 6 the first time, we cannot pick it again because we said it was not replaced. So now there's only 5 cards left in the stack, right? And only 2 of them are even. So our chance of getting an even number the second time is no longer 3 out of 6, 2 out of 5. Okay? Because we took one card out, there's only 5 cards remaining, and since the card we took out was even, only 2 even numbers remain. Okay? That's the tricky part. That's what we're going to practice. Then we just multiply. We can say 3 times 2 is 6. 6 times 5 is 30. And then 6 over 30, we can divide both those numbers by 5. We always want to simplify if we can. And that gives us 1 over 5. So what is the chance of getting 2 even numbers in a row without replacing? 1 out of 5. second. Yeah, 6. Good call, good call. Ha ha ha, I was testing you. Alright, what was that? So second ratio changes. Because first card is not replaced. Alright. And that's about it. Okay. Good luck with that. That's all you need to do for this weekend. So, have a good week.